With the objective function introduced just now, we next see how to optimize it. Let's consider what optimization algorithms can be used. When it comes to optimization, I believe your first thought is likely the gradient-based algorithms, such as gradient descent or gradient ascent. Here, we aim to minimize the objective function, so we will use the gradient descent algorithm. The algorithm's expression is very simple. The parameter we are optimizing is w, so wk plus 1 equals wk minus alpha k delta wj wk, where this is the gradient of the objective function with respect to w. What is this gradient? Let's substitute the explicit expression of our objective function here and calculate specifically. This involves moving the gradient operation inside the expectation and then differentiating to obtain the error, followed by the gradient of v hat with respect to w, and then rearranging a bit to bring the symbol outside. We thus obtain the true gradient. However, the true gradient above involves the calculation of an expectation. How can we avoid this? We can use a stochastic gradient to replace this true gradient. The corresponding algorithm is as follows: wt plus 1 equals wt plus alpha vt, where the long string that used to be inside the expectation has now been simplified by removing it and replacing all the random variables inside it with sampled states st. Note that here we have a factor of 2, which gets combined with alpha k, making the expression look neater. Up to this point, we have introduced the expression of the algorithm, but only halfway. Why is that? Because it involves v pi st, which we don't know. In fact, it's the quantity that we're trying to obtain. So this algorithm cannot be used in practice as it is. To solve this problem, we can replace v pi st with other quantities. How to do that? We have two methods. The first method is Monte Carlo learning, which is very straightforward. Although we don't know v pi st, we can use gt to replace it. What is gt? Starting from st, I have an episode, and along that episode I receive a series of rewards. The discounted return I can get is gt. I use this gt as an estimate for v pi st. Isn't this the basic idea of Monte Carlo? At this point, the resulting algorithm is the Monte Carlo learning combined with value function approximation. What is the second method? Recall that we previously introduced two types of model-free methods. One is Monte Carlo and the other is TD learning. So naturally, the second method is to combine TD learning with value function approximation. Specifically, this algorithm becomes this, which replaces the original v pi st with rt plus 1 plus gamma v hat st plus 1 wt. This is the TD target. This combination actually forms the TD error, and the algorithm is TD learning with value function approximation. The pseudocode for this algorithm is provided here. Let's briefly go through it, although there's not much new to introduce. For an episode and for each step within it, we have such a sample. Then I use this sample to update w. This algorithm can then minimize such an objective function because it is a gradient descent algorithm. You may have noticed that I mentioned in the general case. Actually, there's also an in the linear case which we haven't introduced yet but will discuss shortly. What is the linear case? It's a specific choice of v hat. Until now, we haven't yet discussed how v hat should be chosen. In fact, there are many ways to choose it, such as linear functions, nonlinear functions, and so on. We will discuss these ways later. If it's linear, I can substitute the specific expression of v hat into this equation to get the specific algorithm in the linear case. Up to this point, we have introduced the optimization algorithms, which are actually quite straightforward. I want to emphasize is that what this optimization algorithm does is estimating the state values of a given policy. Later, we will extend this to estimating the action value and then combining it with policy improvement to develop an algorithm that can search for optimal policies. Anyway, the current algorithm for estimating the state values is crucial as it helps us understand the core ideas of value function methods. Just now, we introduced the objective function and the algorithm to optimize it. Later, I will introduce more examples to help you understand better. Now let me talk a bit more about this function approximator. Previously, we mentioned that we use a function v hat to approximate v pi, but we haven't talked about how to design this function v hat. We have touched on this briefly before, but now let's emphasize it. There are basically two methods. The first method was very widely used before. Here, v hat is a linear function, and its expression is v hat sw equals phi transpose sw, where phi is its feature vector. We have already introduced this through examples of straight lines and parabolas in our motivating examples. Here, v hat is a linear function of w, as the preceding can be considered a coefficient. A very important problem is how to choose this feature vector. Of course, there are many ways to choose it. We have also previously discussed how to design this feature vector based on polynomials in the motivating examples, and we will provide more examples in the illustrative example section. Another method, which is widely used nowadays, is to use a neural network as a nonlinear function approximator. That is, I do not know the exact expression of the neural network, but I can input S and it outputs VSW, with W as its parameter. This neural network can be considered as a nonlinear function of W. Now, let's look again at the linear case. If v hat can be written as such a linear expression, I can compute its gradient, which equals phi s, the feature vector. If I substitute this into the algorithm we derive from TD learning with value function approximation, substituting v hat and its gradient, then we obtain the following algorithm. We've already introduced this algorithm in the pseudocode, and here we give it a name called TD linear. I will use this algorithm in several examples to demonstrate the advantages and disadvantages of linear function methods. First, let's talk about its disadvantages. The biggest disadvantage is that we need to choose appropriate feature vectors. This requires a good understanding of the problem. However, even with a great understanding, it's non-trivial to select a good feature vector. This is the main reason why linear functions have gradually been replaced by neural networks. Similar to traditional machine learning, has been gradually replaced by deep learning. Nevertheless, linear function methods still have some advantages. The first advantage is that its theoretical properties can be thoroughly analyzed. If we use nonlinear neural networks instead, the theoretical properties would become much more challenging to analyze. It is a common approach not only in reinforcement learning, but in many fields. Facing a very complex problem that is hard to understand, we often step back and try to understand a simpler version of the problem first. Understanding the simpler problem can help understand more complex problems. Historically, there has been extensive research on linear function approximation, with many theoretical results developed. If you are interested, you can refer to my book. Another advantage of linear functions is their powerful representation ability. Why do I say this? That is because the tabular representation method can be considered as a special case of the linear function method. In this sense, linear function methods can unify tabular representation and function representation of values. Next, let's see why the tabular representation is a special case of linear function representation. First, consider the special feature vector for state S, phi s equals es, where es is a vector with all elements being 0 except for the element corresponding to state S, which is 1. If we choose a feature vector like this, the resulting value function actually becomes a table. Why? If I substitute phi s into v hat, it becomes es transpose multiplied by w. Since in es only the component corresponding to state S is 1, and all others are 0. The result is simply ws. Ws is the element of the vector w corresponding to the position of S. It is clear to see what v hat essentially becomes. It becomes a vector or a one-dimensional table. To find v hat S, we can directly look up the value at the position corresponding to S in the vector. Let's take this further. Here is the TD linear algorithm we introduced just now. When we substitute phi s into it, the resulting algorithm will be identical to the tabular TD algorithm we introduced in previous lectures. Why is that? Let's examine it closely. When we substitute phi st equals es into the algorithm, we get this new expression. Notice that in this algorithm, this is a scalar, this is a vector, this is a vector, and this is a vector. But this vector only has a 1 at the position corresponding to st, with all other elements being 0. Therefore, only the element of W corresponding to ST is updated. All other elements remain unchanged. We can isolate the element of W corresponding to ST, and its update rule becomes WT plus 1 equals WT plus alpha multiplied by this term. This is exactly the same as the tabular TD algorithm we introduced in the past. The only difference is that in the previous algorithm we used V, whereas now we use W. If we replace W with V, we get the same algorithm as before.